Okay, everybody, so we are now talking of unit 5, which is electricity and magnetism. And in this unit we are going to understand only the 5.2 here, which will deal with the heating effect of current. Okay, effect of current. Before we go into this, let us understand certain things or recall some of the basic things. So if you start recalling, if you remember, charge is nothing but property or nature of a substance. So we knew it can be positive charge or a negative charge, and the charge is measured in coulomb. Okay, we have seen in charge that the force of attraction or repulsion is given as K Q1 Q2 by R square, where your K is equal to 1 by 4 pi epsilon naught, and this is called your permittivity, and this has a value of 8.8 into 10 power minus 12. Now this is not actually a very important thing. This whole thing is 9 into 10 power 9. So this is given in data booklet. In this particular topic, that is heating effect of current, we are going to focus in certain topics. So we are going to understand what exactly is current. So current is nothing but, we say, amount of charge flowing per unit time. So I is given as Q by T, where Q is nothing but NE, where N is nothing but your number of charge, and E is charge of one particle, which is 1.6 into 10 power minus 19 coulomb. Now, once you know what is exactly current, we have to now go into the effect of this current. Okay, so we are going to study now the effect of current. There are many effects in this unit, particularly 5.2. we are going to study about the heating effect. Okay, so when we have to talk about heating effect, we have to understand certain concepts here, and one of the concepts that we need to understand here is known as your resistance. Okay, so if you recall your Ohm's law, where we saw your potential difference V, which is your potential difference, is directly proportional to the current, and then we get V is equal to IR, where R is V upon I. So this R is your resistance, right? And this has a unit of volt per ampere, or you can call it as ohm, or you can write the symbol ohm, the omega symbol. Now I can define resistance in terms of V by I, so I can write it as the ratio of potential difference and current, or I can also write resistance as amount of energy lost, or I can write in terms of work done to overcome energy loss. Okay, so you can define in terms of the formula, which is a very easy one. So but make sure that you tell what is V, what is I here. Okay, now let us go a little more ahead. What are the factors actually on which this particular resistance depends? Okay, so resistance of a conductor depends on what are the factors now we have to see. Okay, so first factor is length. If the length will increase, then your resistance will also increase. So R is proportional to L. Second is area of cross section. What is area of cross section now? Area of cross section means it is this area. This is called area of cross section. So resistance is inversely proportional to area. If the area will increase, then electrons can pass little easily, so resistance will decrease. So which means I can now combine both and I can write proportional to L over A. Therefore, I can further write this as resistance equal to rho L over A, which is rho is your resistivity or specific resistance, and it is constant. Okay, so it is constant. So now if you see from here, your rho can be written as R A upon L. So if I have to write the unit, for example, so if I have to write the unit of this particular rho, so unit of rho will be then equal to ohm meter square by meter, so it will be ohm meter. Okay, so there are two formulas now. One is your this formula, this is for resistivity, and then you saw the Ohm's law up, which was for resistance. Okay, now let us go a little more ahead. Now we are slowly going to enter into the electric circuit, and we will see how the circuits are designed, okay, so that we understand better this. Now there are two types of substance. One is called ohmic and non-ohmic. So what exactly are these now? Ohmic are the ones which obey Ohm's law, and non-ohmic are the ones which do not obey Ohm's law. Now if you see the diagram, then in this case the graph between V and I will be a straight line, whereas in this case between V and I may not be a straight line. It can be anything. It can be something maybe like this, okay, a curve. So not a linear graph at all. Now what sort of substance behave as non-ohmic? That is a question. So semiconductors behave as non-ohmic substance. Your electric bulb, when temperature increases, that also behaves like non-ohmic, right? So if I have something like, say, a graph, in the beginning it obeys and then it doesn't obey, so till here it obeys, then at very high temperature the bulb does not obey Ohm's law, okay. Now this is about the ohmic and non-ohmic. All right, so resistivity is seen, resistance is seen. Now we are going to just briefly see about the series and parallel, and then we will go ahead with the other topic. So let us come with this series and parallel now. Series and parallel connection. So if you remember, in the series connection, the resistors would be connected one after the other, right? And then we connect that to the power source here, which is the voltage we are supplying. And this is R1, this is R2, this is R3. The interesting thing is, this is positive, this is negative, and the current direction is going this way. So current is going this way. Now current does not get divided here, okay? Because current remains same in series. Potential difference rather is divided, because the electron which goes from here has to give some energy to R1 and then only carry the remaining to R2 and R3. That's how it goes. So which means I will have here different voltages here. So I will have maybe here V1, maybe here V2, maybe here V3, which means I am going to have V is equal to V1 plus V2 plus V3, which means I can write this as IR equal to IR1 plus IR2 plus IR3, which means I can write it as just R equal to R1 plus R2 plus R3. So this is the equation that we have for series connection. Okay. Now coming to parallel connection. If you come to parallel connection and if you do that, so in parallel what are you going to have? You are going to have like this, and then you will have another one like this maybe, right? And then you are going to have the voltage source like this, so which is V. And then you have your R1, you have your R2, and then again positive, negative, and the current flows here. But if you look at these points, they are called junctions. Junction. Okay. So at junction, the current divides. Now that means what? If I have I here, it will become as your I1 and it will become your I2. So your I will be equal to I1 plus I2. According to Ohm's law, your V was IR. So your I has to be then V upon R. So which means I can write this equation as V by R equal to V by R1 plus V by R2. Which means I can write this as 1 by R equal to 1 by R1 plus 1 by R2. So this is the equation I get for your parallel connection. Okay. So this is series connection and this is parallel connection. Now let us go ahead a little bit more. Okay. So if I go here now, I am going to further again understand a little bit differently now. So I know the series, I know the parallel. So if I have a question, let's say for example, and if I am asked, okay, you are having 2 ohms, you are having 3 ohms, and let's say you are having here something like 10 ohms, and then you are connected here with the source here like this. And if they ask you, find out the V1, find out the V2 and all those stuff, maybe find out I1, find out I2, how do we do now? Now this is positive, this is negative, this is 12 volt. So the current will go from here, here comes your junction, right? Here also you have a junction. So obviously your current is going to be divided now. So if you are having a current here as I, is going to become as your I1 and will become current as your I2. Okay, so in this circuit now, my series connection, I have 2 plus 3, which is 5 ohm. Now I will go for the parallel connection, resistance. So in parallel, I have 1 by R equal to 1 by 5, which I got here, plus 1 by 10. Why is that? Because top, I have made him now 5 ohms by combining, and then I have my 10 ohms. So that is why I have to make this. And then I have that voltage supply, which I have given 12. So if I do this, then I am going to get here 10, and then it becomes 2 plus 1. So it is 3 by 10. I have to do reciprocal, so which means R will become 10 by 3. So that is 3.3 ampere approximately, right? So now if I go back here and if I have to solve your remaining questions here, so if I come at this point, okay, how am I going to distribute now? Let us see. So what is the total current now? Total current will be total voltage by total resistance, okay, which means that is equal to your 12 volt by your 3.3, correct, or 10 by 3, which becomes your 36 by 10, which is 3.6 ampere. So I have here now 3.6 ampere, okay. After this it will get divided here. So let us find out first this. Because they are parallel, it means the 12 volt will come here as 12 volt and here it will get divided. So among these two, the 12 volt will get divided now, okay. That I will come later, but I know here it is 12 volt, this 12 volt. So I am going to use this 12 volt and calculate the current here. So my I1 will be equal to the 12 by the resistance, which is 10. So he is going to consume this much current. Therefore, what will be then I2? Then I2 will be 3.6 minus 1.2, which is 2.4 ampere. Makes logic sense? So which means here I am going to have 2.4 ampere. Here also I am going to have 2.4 ampere. Here also I will have 2.4 ampere. Here I will have 1.2 ampere. And then they will combine and become again 3.6 ampere. See? So here I know it is 2.4 ampere and I also know that it is 2 ohm. Can I find the V1 now? V1 will be IR. So which means the current there is 2.4 into the resistance, which is 2. So that makes him 4.8 volt. And then V2. So V2 will be again same thing. So it will be 2.4 into 3. So that means it is 3 4 12, 7.2 volt. Then if I do V1 plus V2, I will get my 12 volt. See? So that's a correct answer, right? So which means this is how you have to solve the question here in this simple circuit. So that is one thing that we have seen. Now coming to the electric power, let us say. So if I have to think here, electric power, okay. Now if I talk of electric power, power is nothing but basically work done by time. And this potential, the voltage is given as your work done by charge, which means now I can combine these two and I can write the power as VQ by T. If you look here, this term is nothing but actually your current. So I can write power as V into I. So this is the formula of the power, right? But Ohm's law says that V is equal to IR. So which means I can write my power also as V square by R, or I can also write I square R. Anything I want, okay? Then what is my electrical energy then? Then my electrical energy technically then would be your power into time. So power is, if it is VI, then VIT, or it can be I square RT, or it can be V square by RT. So any one of these can be the electrical power, right? And my efficiency in this electrical thing is again same. So it is nothing but output which is useful by input, which is total, right, into 100, that much. Now this is one part of this thing. We have to now go inside the electric circuit, okay? So I'm going to further go inside this circuit. Now we have different type of resistor. Before I get inside the resistor, you have to understand that electric circuit with resistor as potential divider. So potential divider is basically important for you here in the syllabus, okay? So I'm going to discuss that now. Let's start. Now electric circuit, we know, we have seen that up, right? How is it potential divider? So I'm going to draw a circuit now here, and in this circuit I am going to have the cell up, and then I am going to have one resistor here as R1, and I am going to have another resistor here as R2, and then I will have like this. Okay, so I am going to supply something called your voltage here, which is V. Okay, sometimes we also call this as EMF. If you remember, EMF is amount of work done to move unit charge when circuit is open. When circuit is open. Okay, and don't forget this is very important. Now what I am going to do is, my job will be, I am going to find out what is my voltage V1, what is my voltage V2. Okay, this is positive, this is negative, so current will flow like this. You agree that? And this is called what? This is called your junction. Once you come to the junction, then the current which was coming here, I, has to now divide. Okay, so let me use different color because that will be easy for us to understand also. So I will use here maybe blue color little bit. So okay, so I will use here I1, sorry, not I1, I will just okay, so I'm going to use here I, and then I will put here as I1 and I will put here as I2. Okay, so just one second, I'm not going to put this. So yeah, okay, I'm not going to do this I1 and I2 business. Let it be I just now. Okay, just now. So if you look at this circuit here, what do you see in the circuit now? You can see in the circuit that total resistance is R1 plus R2. Then what is the total current? Total current will be total voltage by total resistance. Make sense? So which means I can write I equal to V by R1 plus R2. Just keep this in mind. Okay, I am going to find V1 now. So when I find V1 will be equal to I R1. Why? Because I is same. And why is I same? Because R1 and R2 are in series connection. Okay, series connection. Therefore my V1 will be equal to I, but you look at the I here, it is this. So I can write V by R1 plus R2 into R1. So look at this equation now. This is the equation. So this equation is going to play a very crucial role. So the full voltage, the voltage or the potential difference V is divided using resistors, and this system that we have created is known as potential divider. I will draw a different diagram of this little later. Potential divider. Now come down little bit more. If R1 increases, you see, if R1 increases, your V1 also increases. Correct? If R1 becomes too big compared to R2, too big, then R2 becomes almost negligible. So we can ignore this then, R2. In that case, what are you going to get then? Then you will get V1 equal to V by R1. So it will cut, which means your V1 is almost same as V. So for very high value of R1, the input voltage is fully or maximum consumed by R1 itself alone, just R1 itself, right? So keep this in mind. Okay, now so R1 is a key role here. So if you have seen just now that as your R1 will increase, your V1 also increases. If R1 becomes too much big of R2, that R2 becomes very small, we can neglect him. Then that means the complete input voltage that you are giving V, this is the input voltage, right? So this V is now taken by V1. Complete, it's same. So full voltage almost goes into overcoming the resistance R1 only. So there's nothing left for R2 almost. Okay. Now I will come to the sensors. Okay, there is something called sensors here. So let us say we will talk of some of the sensors. Okay. So first sensor, let us talk of thermistor. Thermistor. So thermistor is a resistor, rather a device where when temperature increases, the resistance decreases. Okay, so it's something like this. Say this is a thermistor, and for some reason you are increasing the temperature. So what will happen is a lot of electron inside. So as you heat, this electron will move freely. Electrons start moving, which means what? Which means your current increases. What does it mean? Resistance decreases. See? Okay. Now, if I have to design a circuit where I have this cell or any input that is available, this is the voltage input, let's say, and then I have this thermistor here, the device. So I have a thermistor device which is shown here like this, let us say, and then I have another resistor here. Okay, so this is R1, this is R2. My R1 here is my thermistor. Okay, R1 is thermistor, right? And just now we saw up, what did we see? We saw R1 was equal to V by R1 plus R2, correct? And then you had again R1. Sorry, again you had there V1, sorry, my bad. So I'll just erase this and write it here as V1. So that is V1. Okay, so this was the equation we derived up, right? Now if temperature increases, resistance decreases, then V1 also decreases. But if temperature decreases, resistance increases, which resistance? R1, by the way, R1 increases, then your V1 also increases. And if temperature is very high, then what happens is this is your input, so your V1 almost becomes equal to V input, which means no current flows, no potential difference across R2. Now this difference in the voltage that you are seeing in thermistor causes an alarm. So if house is in fire, the heat sensor experiences a sudden increase, sudden decrease of voltage. This case here, so temperature increase, R1 decrease, V1 decrease of voltage. This change in voltage causes the alarm to ring. Okay, so this is how your thermistor works. Now exactly same way, we have another device which is called LDR, which is nothing but your light dependent resistor. It's just like some sort of semiconductor, and when light falls, the electrons move, so resistance decreases. Okay, resistance decreases. What does it mean? If resistance is decreasing, then your voltage is decreasing. See, so again there is a decrease in the voltage. Now there is a change in the voltage, which means delta V. So again, because of this, the same thing can happen. So if you have excess light or no light, let us say, so if there is a zero intensity, then what will happen? Resistance will increase, so voltage will increase. And if it is maximum intensity, then resistance will decrease, voltage will decrease. So this is how your actually LDR works and sensor works based on this idea. So circuit is same, only thing is in a LDR circuit what you are going to have is just the device will look different, that's all. There is nothing big thing in that. So the device will look something just same circuit. So I will have this V input and I am going to have the LDR here, and then LDR is something like this, and then I have this light coming here, and then I have the second resistance here. So this is just like R1, this is R2, and everything is same, no problem. Only thing is this fellow is an LDR, that's it, the first one, and everything works exactly the same way. You get your V1 here, right, and all the formulas are same here. So this is how it works actually. So you understood now what is the potential divider, okay, and you understood what are the sensors and what are the users here right now. So let us go a little more ahead here and let us just see if you can understand this part, which is complete circuit diagram for potential divider. Okay, potential divider. So if I have to put this complete diagram for potential divider, I have to draw it something like this. So I have a cell here, and then I'm going to have resistance here. Okay, so this is my V in, positive, negative, this is my current, this is my current, going like this. I am going to continue here. I am going to have a resistor or a bulb, and then I am going to have here an ammeter, and then I am going to connect here with a jockey. This is a jockey or a piece of wire. You know, this is nothing but a wire which if I touch here, then I am dividing him into two lengths, see, L1, and I am dividing him into L2, and I know that my R is rho L upon A. So I very well know that resistance is directly proportional to L. So if my L1 is bigger than L2, greater than L2, then my resistance R1, which is for this L1 here in this region, will be bigger than my R2. So by manipulating the length, I am manipulating the resistance. Okay, so the ammeter is always to be connected in series, and then if I need a voltage across this bulb, I have to connect this. So there is a junction here, okay, and then the current gets divided here, I1 and I2. So this will measure your I2. Okay, and if you want here V, then you have to do I2 into his resistor, let us say R, so his R. That is how you have to find the voltage here. Alright, so this is how the circuit technically works actually. And 1 second. Yeah, okay. So what we have to observe here now? You have to observe certain things here, which is very important for us. Note. What we have to note here? Note that R1 and R, the bulb, are parallel, which means if I have to do the total resistance for the parallel, it will be 1 by R1 plus 1 by R of the bulb. This one, okay. Now, if I do this, let's say for some reason the R of the bulb becomes very high. It becomes something like say 100 kilo ohms, which means it is almost like 10 power 5 ohms, right? So what will happen here is, now your 1 by Rp will be equal to your R of the bulb, R of 1 by, sorry, in between I have to put plus, and then I have to put here R1 plus R of the bulb. So which means I have to reciprocal it and then put Rp, which is equal to your R. There's error here, 1 second, just wait. Okay, I have to remove this. Okay, and then this is times, so I have to put here R1 times R of the bulb by R of the bulb plus R1, which means what? If R of the bulb becomes extremely high, then Rp also will become very high. Then Rp will become very high, because of this will become very high, right? So according to that, you have to decide what is going to happen. Okay, so if your resistance, this R, becomes too high, then in parallel condition, if you see here, then your parallel condition, it will become 1 by very high, this value. Okay, and then so this is done. Now another note is if L1 becomes 0 centimeter, then R1 will also become 0 ohms, correct? Then only R2 will have the role. See, so that can also happen. You can manipulate this fully from here to there. So this is all about your circuits. Now the last part that we are going to discuss here is your Kirchhoff law, and then we are done. So in the Kirchhoff law, if I talk of the Kirchhoff law, let's discuss now Kirchhoff's law. So there is a circuit here, and there is a bulb here, and this is the EMF, and this is the voltage the bulb is consuming. So we know that this will be equal to this if the internal resistance is 0, where this is your internal resistance. Okay, in that case I can write this as, shift it here, so I can put it as plus of minus V equal to 0. So this can be now written as sum of EMF in closed loop is 0. That becomes one of the law for him. So this is the second law of Kirchhoff. The first law says if I have a current which is coming here, I, there is a junction here, and then the current gets divided here and here as I1 and I2. I can write I equal to I1 plus I2. Okay, so this is also another law now. This became another law, this one. So this is your first law and this is your second law. There are two laws now. How do I apply it? Before I apply it, there is a rule here. The rule is like this. The rule is something like this. One second, just it went down here. Okay, so the rule is, if I have a circuit, rule, I am going to make the self rule first. So I have this, I have my resistor EMF, and I am going to decide that I will move it clockwise. Okay, so I have decided to move clockwise. Okay, now if my direction is from positive to negative, if my direction, please note here, if my direction is from positive to negative of cell, I will take EMF as plus E. Okay, so this is my rule number one I have set. Second rule I am going to set. Now the direction of the current is going like this, see. So if my direction goes opposite to the direction of current, now this V is IR. So if my direction is opposite to current in circuit, then I will take negative V or negative IR. Okay, so I am going to use this now for working on the diagram. So let me just go down. Yeah, okay. So I am going to take a circuit now and then I am going to work here. So let me just draw one circuit here. So if I take a circuit, let's say here R1, then R2, R3, then I come here, I have this, and I have this, and let's say this is like something like a 12 volt, and this is V in we are giving. So this is positive, negative, so the current is flowing here, current is flowing here, which means I am having I am having I am having I, and then I get a junction, so it becomes now maybe I1 and maybe I2. Okay, what does it mean? It simply means my I is equal to I1 plus I2, so I will have it as my first equation. Okay, and then this current goes here, 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 like this, and then they mix here, and then they again become here I. Okay, so this is I2 and this is I1. Now I am going to take here direction. So I am going to take here two loops inside this. I am going to take them again clockwise, like this, clockwise, like this, like this, like this. And I will name this as loop 1, I will name this as loop 2. Now I will start working with it. So in loop 1, let us say, in this loop, what's going to happen now? See, I am moving from, my direction here is from negative to positive. So my direction is from negative to positive of source. Did you understand? So my direction here is going from negative to positive. See, I am going like this direction. Okay, negative to positive. And then up here, we already decided one rule we made here. If I go positive to negative, then plus E. So which means if I go negative to positive, I have to take minus E. So now this V will become my minus 12. Okay. Then I have to take this as minus E. Like that. According to the rule. Now if I go slowly up here, my direction and the current direction are same. See, both are same. So even if I write here V, which is I R1, okay, and if I come here and write V, I have to write here I2 R2. So if I look at R1, my direction and current are same. So I have to put here plus I R1. Why? Because my direction is same as current. Because had it been opposite, here you see, if my direction is opposite, I should have taken negative. But that is not the case. My direction is same as that. So I have to take this only. Now come to the next part here. I am moving down, current is also moving down. See, both are same. So again I have to take this as positive, which means I have to take again plus. I have to write here I2, I have to write here R2, and then I have to put 0. So exactly same way I have to do now in loop 2 also. In loop 2 again, so I have 2 now here. So I can write here also V is equal to I1 R3. See here, I am going up, I2 is coming down, right? So I have to now take this one as my minus I2 R2. Why? Because we are opposite direction. We are opposite direction. Which my direction is opposite to the current. I am going up, current is going down. That is why he is negative. Because up here we decided if they are opposite, then we are going to take that as a minus value. Okay. Now come to the next one. So next one is this. My direction and the current direction both are same here. So which means I have to put here plus I1 R3. Why? Because same direction. This is same direction. You see here? So this is my direction and this is the current direction. Both are same in the same side. So I have to take positive and then I put 0. Now this becomes my equation 2. This becomes my equation 3. All I have to do is now solve simultaneous equation. So I have to just do simultaneous equation to find I1, I2, I in the circuit. So this is how we apply the Kirchhoff rule here. Okay, and I think now this should be very helpful for you. So maybe you can try some of the notebook questions also, I mean a textbook question also, and then maybe you will understand better how to solve this. Okay, so I think this it will end here. It will end here, and all the best. So I'm going to stop.